Hello everyone, welcome back to the channel. Today we are solving LeetCode problem 960, delete columns to make sorted 3. You are given an array of n strings called strs, and all the strings have the same length. You are allowed to choose any set of column indices and delete those columns from every string. After deleting the selected columns, the remaining characters in each string keep their original order. For example, if the strings are ABCBF and UVWXYZ, and we delete columns at indices 0, 2, and 3, the final strings become BEF and VIs. Now here is the main goal of this problem. After performing deletions, each individual string must be in lexicographic order by itself. That means for every row, the characters must be non-decreasing from left to right. So for each string, character 0 should be less than or equal to character 1. Character 1 should be less than or equal to character 2, and so on. Your task is to return the minimum number of columns that need to be deleted to make this possible. This problem is different from the previous versions because now we are enforcing lexicographic order within each row, not between rows. In the next part, we will look at examples to clearly understand this requirement and then move on to the solution approach. Now let us go through the examples to understand this problem clearly. Example 1. The input strings are BABCA, BBAZB. We want every individual row to be lexicographically sorted after deletions. If we delete columns at indices 0, 1, and 4, the strings become BCAZ. Now check each row separately. In the first row, B is less than or equal to C. In the second row, A is less than or equal to Z. So both rows are individually sorted. It does not matter that the first row is greater than the second row, because row-to-row order is not required in this problem. We need 3 deletions, so the output is 3. Example 2. The input contains only one string, EDCBA. This string is strictly decreasing. To make it lexicographically sorted, we must keep only one character. That means we have to delete 4 columns. So the output is 4. Example 3. The input strings are GHI, DEF, ABC. Now check each row. G is less than H, and H is less than I. D is less than E, and E is less than F. A is less than B, and B is less than C. All rows are already in lexicographic order, so we do not need to delete any columns. The output is 0. These examples highlight the key difference in this problem. We are not comparing rows with each other. We are only making sure that each individual row is sorted from left to right. Next, we will look at the solution approach and see how to solve this efficiently. Now let us break down this solution step by step and understand the idea behind it. This problem is actually a dynamic programming problem, and the key insight is to think in terms of keeping columns, not deleting them. Instead of asking which columns to delete, we ask what is the maximum number of columns we can keep so that every row remains lexicographically sorted. Core idea: if we keep a set of columns, then for every row, the characters in those columns must be non-decreasing from left to right. So the columns we keep must follow a certain order that works for all rows at the same time. This is very similar to finding a longest increasing subsequence, but applied to columns instead of numbers. Step 1. Basic setup. We store n as the number of columns, m as the number of rows. We create a DP array of size ed. DPI represents the maximum number of columns we can keep ending at column I. Initially, each column by itself can always be kept, so we initialize DP with 1s. Step 2. Building the DP. Now we iterate through columns from left to right. For each column I, we check all previous columns J, where J is less than I. We want to know, can column J come before column I in a valid kept sequence? Step 3. Column compatibility check. For columns J and I to be compatible, for every row R, the character at column J must be less than or equal to the character at column I. If even one row violates this, we cannot keep both columns in this order, so we loop through all rows and verify this condition. Step 4. Update DP. If column J can come before column I, then we can extend the sequence. So we update DPI equals the maximum of its current value and DPJ plus 1. This is exactly the LIS pattern. Step 5. Find the best sequence. After filling the DP array, we find the maximum value inside it. This value represents the maximum number of columns we can keep. Step 6. Final answer. The total number of columns is n. If we can keep mx columns, then we must delete n minus mx columns, so we return n minus mx. Time complexity is columns squared times number of rows. Space complexity is linear in the number of columns. This is a classic dynamic programming pattern, once you recognize it as a longest increasing subsequence on columns.
Alright, now that the solution is complete, let us go ahead and run the code. Nice, all the test cases are passing successfully. That confirms our dynamic programming approach is working correctly. Now let us hit submit. And there we go, accepted, all test cases passed. That wraps up LeetCode 960 delete columns to make sorted 3. If this explanation helped you, make sure to like the video, subscribe to the channel for more daily LeetCode walkthroughs, and I will see you in the next problem. Happy coding!